Okay. Again, good morning. And welcome to the data science class. And this is our week 4, and we're going to be focusing a little bit on AI, starting from, the very basics. So I'm going to be sharing my screen, and our focus today would be understanding the various types of AI. I'm probably not going to talk about what AI is and all of that because I know most of us are, it's an AI world, and a lot of us are already steeped in what AI is. But what I'm going to be doing today is just focusing on some of the things that I think will be very relevant to our data science work and eventually some of the certificates we would be working on later in the class. So this is what I have. And if you have any questions, you can include it in the chat. I will be monitoring the chat too. So let me see. So if you are looking at this, I know it's kind of the color seems a little bit sharp from my end, but I hope you can still see what's going on here. So, and I'm going to be, in terms of artificial intelligence, kind of breaking it up along the lines of categories and algorithms, right? And there are two main categories of artificial intelligence. You have your machine learning and deep learning. Now, um, don't don't worry about the definitions and all of that, because if you go too deeply, what we have is usually you have artificial intelligence, and then under artificial intelligence, you have machine learning, and under machine learning, a special type of machine learning is called deep learning. So whatever categorizations I do here are kind of a little bit loose, but we're doing it this way because I just want you to get a general sense of how things are arranged around artificial intelligence. So essentially, we'll start. Let's again, deep learning in true definition is a subset of machine learning, is a special type of machine learning. So, but for the purposes of this class, I want us to just look at artificial intelligence broken up into machine learning, and then you have deep learning, right? But under machine learning, you have different kinds of machine learning, right? You have supervised learning, and then you have unsupervised learning, and then you have reinforcement learning. Um, when it comes to analysis of data, or generally data, all of this, all aspects of machine learning can be very data hungry. You need data to be able to do most of what you're doing. In fact, if there is no data, I would probably say there will be no artificial intelligence, right? But then you have your supervised learning, and then you have unsupervised learning, and you have reinforcement learning, and then here you have deep learning. But notice something that I will show you right now. And that's why I said deep learning is a subset. Deep learning is a subset of machine learning. So notice something here that I say neural networks, right? You see neural networks, but also come under here and see neural networks, you know? So in a sense, you can actually draw a broken line from this point to this point. But because we don't have enough space on one page, it's already squished, right? So deep learning is actually mostly driven, most of what you learn in deep learning come under the classification of, in terms of the algorithm, under the classification of neural networks. And then this place, it now shows you the different kinds of neural networks, and we would go a little bit into those later. So you have your artificial neural networks, convolutional neural networks, recurrent neural networks, and then transformer. Transformer systems are, if you think of your chat GPT, right? You have your chat GPT, and then you have the Google one, and then different people are coming with their own generative models, right? And large language models, a lot of it, right, is run under transformers are a kind of algorithm that makes all of those things possible, right? And then what else do we have? Under supervised learning, you also have linear regression. We're going to look at a bit of linear regression today. We're going to look at logistical regression, and then you have decision trees, you have random forests, and support vector machines. A lot of those are all supervised kind of learning. And what actually makes this in supervised learning, right? And I'm going to talk about that a little more as we go down the slide. So no need to dwell on it here. And then you have unsupervised learning, right? You have k-means cluster, hierarchical cluster, principal component analysis, and autoencoders. And then, of course, you have reinforcement learning. So I'm going to go down and let's begin to break all of this down a little bit because it would be helpful. Let me see. Now, it seems like I'm frozen. Okay. So first of all, what is supervised learning and how does it work, right? So supervised learning is a type of machine learning where AI learns from labeled data. So essentially, you give it data, right? And you tell it what that data is, right? So um, it has all of the information it needs to learn, right? So if I want to teach a child, maybe a child that is 8 months old, 1 year old, I will show them an apple and I'll say, this is apple, 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 right? And then you bring a mango and you show them this is mango. And then you bring something else. So you are not only giving them you're not only showing them the fruit, but you're also providing the label to that fruit to be like, okay, this is this. And over time, right, the child learns that this fruit that looks this way is actually an apple. And that's just essentially what supervised learning is. So it means that the data already has the correct answers or the labels, and the AI's job is just to learn the patterns and make predictions on new unseen data. So that's essentially what supervised learning is. Again, here it says, think of a teacher and a student. Imagine you're learning math in school, and your teacher gives you a set of math problems along with the correct answers, right? You go ahead and you study these examples, you understand the patterns, then you use that knowledge to solve new problems. So, the teacher teaches and then they give you examples of how you can solve that problem. But then um, on the day of exam, they don't give you exactly those questions, right? They give you variants of those questions. But if you have learned the principles and you've learned the details, patterns and everything about the exams, in-class examples, you probably 90% or more can actually solve the problems that come up in the exam. So that's an example of supervised learning, right? And then notice something, right? When there's a reason why the teacher doesn't come to the exam and gives you exactly what you learned, right? If they do that, right, they haven't really done what they are supposed to do as a teacher, because what a teacher does is they give you some of this training data, right, which is what's going on here, and then they teach you all of that, and then they give you completely different but related questions. And with those related questions, the teacher is able to figure out if you learned the principles, not following exactly what was given you in this particular case. So in the case, in terms of AI, right, what the teacher gives to the student at that particular time, right, is essentially training data, right? And then there is a learning phase. The student is able to learn all of that, but then they now give them a different set of questions, right? And they are able to learn. So eventually, one of the things you're going to see in AI is you're going to hear about uh, training data, you're going to hear about validation data, you're going to hear about testing data. And we're going to talk a little bit about some of those in the future. So, for example, training data, you give AI thousands of pictures of cats and dogs, each labeled as either cat or dog, right? The AI looks at the patterns, things like the fur texture, the ear shape, the body shape. And for each of these animals, right, all of those things are different and learns what makes a cat different from a dog. Now you show the AI a new picture, and then, it's able to discriminate, but sometimes it does make mistakes. And when it makes mistakes, you correct those mistakes, right? And give it back that information, and then it gets better and better over time. So the way it learns is not completely different from the way, for example, you train a dog, right? Or the way you train a little child. Same thing, and that's all supervised learning. So now there are two main types of supervised learning. You have classification and you have regression, right? And what is classification, right? So classification, you are essentially beginning to, you are essentially trying to differentiate between one thing or the other. So is it a cat or a dog, right? Is it a man or a woman? So most of what you're doing is you're classifying, or you're putting things in categories. That's what classification is all about, right? But when it comes to regression, you're essentially trying to predict. And I will show us examples, right? And you're looking at continuous data, right? Where you're trying to, excuse me, you're trying to predict something, right? You're giving all of this data. For example, maybe in high school, if you remember, right, you have a situation where you have a set of data and you're plotting a straight line. You have your X and your Y axis and you're plotting a straight line, right? And you're trying to predict if X is this, then Y is going to be this. If Y is this, is X is going to be this. That's essentially regression. So these are all real life examples of supervised learning, right? Um, for example, Gmail uses supervised learning to classify emails as spam or not spam. So if I'm using spam filters, right, for Gmail, what am I using? Is it going to be classification or regression? Any thoughts?
Classification.
Correct. That's classification because you're trying to check whether it has spam or it's not spam. Um, for example, then you also have facial recognition, you have medical diagnosis. You see where we are trying to detect cancer, for example, that would also be a case of classification. So unsupervised learning. Now, like I talked about how you can literally map, you give it something, give it data, and then you label that data and you say, okay, this data means this means this, and that means this. But in unsupervised learning, it's a type of learning where you have the data, but the AI or the machine doesn't know what that data is. So instead, it tries to figure out what the pattern. And one way to look at it from a human perspective is like in the Montessori education system, for example, where you give kids all kinds of things to play with. So imagine if you came in a room, right? And then you have all these toys, and those toys happen to be shapes, right? You have some that are round like balls, and then you have squares, you have rectangles, you have triangles, and they are all there, different colors and different shapes. And then you bring in a little child in there and you tell the child, please sort all of these things out, right? And then the child or the children just come in there, and all the round balls, they put them in one bucket, and all the square balls, they put them in another bucket, and all the rectangular balls, they put them in one bucket. That's essentially unsupervised learning, right? They don't know what those things mean, but they are kind of using the similarities around those objects. In this case, it could be their color or their shape, right? To put them in different boxes. So that's unsupervised learning, right? So AI learns from data that has no label, meaning that AI is not told what the correct answers are. Instead, it tries to find the patterns, group similar things together, or discover hidden structures in the data on its own. So that's unsupervised learning. So think of and this is probably the kind of example that I talked about. You know, you have these jigsaw puzzles, they are different shapes, and you have to sort them, you know, one from the other. So, and of course, you don't know what if you're given a pile of all of these things that you can see in this shape, you don't know what the picture is going to look like, right? But guess what? All you need to do is you begin to bring all the pieces and begin to put them together. Before you know what's happening, you've been able to develop the face of a man or the face or shape of something, right? And but you never knew where you were going before, but all you did was just begin to look for patterns and connect those patterns. And that's how unsupervised learning works. So um an example here will be like you give AI thousands of animal pictures, right? But instead of in the case where you labeled it, this is a cat, this is a dog, you don't give it anything, you don't tell it anything, right? And all of a sudden it begins to look for those patterns, things that are similar. So for example, the ear of a dog is going to be different from the ear of a bird. And then it's looking at all the ears, right, that are similar and putting them. So one of the things that happens is in unsupervised learning is you have a lot of pattern prediction recognition. You have grouping, you're creating clusters and putting things together, right? And then when you get the result as a human, you can now go in there, you know, to make sure that there are that the patterns that have been put together, because a lot of times as the human you don't even know what you're looking for, but the system can quickly sort out all of those things and you can go look at them and then you can confirm that it has done what it's supposed to do. So there are different kinds of unsupervised learning. One of them is clustering. You know, in this particular place the AI groups similar data points together, right? And association. So for association, what AI does is essentially begins to look for relationships between things. And Amazon recommendation engine does that a lot, where you know it looks for people that say bought a particular product, right? If all of these people bought product A and most of them are also buying product B, then that means there has to be a relationship there, right? It's looking for that those relationships to make recommendations. So if a lot of people bought product A and those people are fond of buying product B, then what I would do is I will look for all the other people that bought product A that haven't bought product B. That means these people that bought product A would likely want to buy product B because that's the way people that buy product A behave. And that's association. Okay. And look at these are all examples where in real life, right, where businesses use unsupervised learning for customer segmentation, you know. So for those of you that are in business or something, right, a lot of times to be able to sell effectively to different people, you have to put them in different segments, right? So the Uber affluents, they have completely different buying behaviors from people that are poor, or you have women buy completely differently than men and all of that, right? And when you put all of that data to an AI model, it's actually able to discriminate. And then with that, you can do specific targeting of your customers. So again, as we talk about this, think about all of the data you have and how all of that data you can apply AI using unsupervised learning to be able to make those discriminations and target specific segments uh, uh, of your target community. So anomaly detection too. If there's unusual behavior, right? That's an example of unsupervised learning because it's looking for irregular patterns. So you set it up, it has identified all the regular patterns. If it sees something that is not normal, it will detect it immediately because it already has an understanding of regular patterns. So if it sees a pattern that's unusual, it will flag it. And then things like topic modeling, where AI all of a sudden can put things in clusters, right? And that's why you see a lot of the device in social media, where people that talk in a particular way, AI is aggregating certain kinds of data for them or to them because it's just looking for patterns. So all the angry people, it will feed all of you the same thing. All the happy people, it will give you the same thing. All the conservatives tend to be hearing the same thing, and then all the liberals tend to be so. And that's just the unsupervised learning at work there. So this is one part we are not going to do a lot of work in, but very, very important. Again, that's reinforcement learning. And you can see, like, one of the clearest examples of reinforcement learning is a dog, right? So you ask a dog to do something, it does that thing, and you pat its back, and you be like, good boy. And then it begins to learn that that's a good thing to do, right? Or it does something you don't like, and then you shout at it, or you say something to it, right? Or you frown at the dog. The dog is able to get all of those, right? And as you keep training that dog, or you give it a treat, right? Those things that reward, it keeps doing those things more and more. And I think I have some examples of reinforcement learning. And if you all are interested, I can share like Jupyter notebooks of examples of reinforcement learning. So that's exactly, how reinforcement learning works. So, for example, you tell the dog, sit, sit, sit. If the dog sits, then you give it some treats. And if it doesn't see it, then you're mad at it. And then that's how the dog learns. And machines have been trained to also behave in those ways, right? So you see some of the things about machines, when you go into reinforcement learning, you hear about state, action, reward, and learning. And then you hear things like policy, because you have to tell it so what you want it to do. And then you have positive reinforcement, negative reinforcement, and that's actually how driverless cars work. Robotics, especially when you're AI powered robotics, and stock trading, right? You reward it for doing certain things, and it does more of those things more and more. So there are so many examples of reinforcement learning, but I think that's where I will stop with this. So does anyone have any questions? That's a quick introduction to the different types of AI, or the most popular types of AI. Any questions?
Yes, I have, sir.
Yes, sir.
Yes, sir. So thank you very much, sir. So I have two questions. I already posted one, and
Okay.
the first one is I while you are explaining the regression and the on the unsupervised learning, supervised learning and regression. So I was trying to see if there is a relationship between the two. So what came to my mind is that is it possible for us to, since the concept of regression is actually predicting
Right.
what is going to be the next one. So can we have unsupervised regression? So that's my first question. Then the
Oh,
second one is
yeah. Yeah, go ahead.
what is the okay? Okay, the second one is what is the major difference between reinforcement learning and supervised learning? Though I know that in the second case, reinforcement learning, we are giving incentives, we are giving a reward, or whether negative or positive. But at
Right.
the same time, is that not a way of telling the system, like as a similar case with supervised learning, and this
Mm.
is right, then this is wrong? So what's the major difference, sir?
Okay, so I think I understand what you're talking about. Again, you're talking about like the reward system, right? So, and you're trying to make a distinction between supervised. Oh, are you talk
Yes,
are you are you
yes.
are you trying to make a distinction between
For the second
unsupervised?
one, I'm trying to understand the difference. For the second one, I'm trying to understand what I should understand as the difference between reinforcement learning and supervised learning.
Okay. So re supervised learning. right? Which is where you have your regression analysis. You know, the key difference there would be, again, supervised learning, you already know the outcome, right? There are a lot of similarities for all of them. So in supervised learning, what you're looking for patterns, right? In unsupervised learning, you're looking for patterns. And in reinforcement learning, you're also looking for patterns. The difference is just how you look for those patterns, right? Because in supervised learning, what's happening is you already know what your end goal is, right? Your end goal is very clear at this particular time. But that's not the same thing that is happening with unsupervised learning. In the case of unsupervised learning, you have no answers. You don't know what's going on. And often in unsupervised learning, you need a lot of data, right? And then for reinforcement learning, again, there are a lot of similarities because you're looking for patterns. But the difference in reinforcement learning is the intelligence is developed over time, right? Because the options are just so many that it's not something you can do with supervised learning. And in any case, you don't even have the labels, you don't have the answers. So when you don't have the answers, even though you're looking for patterns, you have to use algorithms that are able to help you achieve what you want to achieve. I don't know if that answers your question, but one of the things that is going to be clear as you begin to look at this is each of
Hello?
them, yeah, each of them, what makes the distinction is the specific algorithm that you're using to try to solve your problem. The specific algorithm that you are using, because the algorithms are completely different things. They are going about the business of trying to solve those problems in completely different ways. Does that help?
Yes, very well, sir. Thank you, sir.
Okay.
Hello, sir.
Yes, sir.
I just, sorry, please just help me a little bit. I didn't get the explanation between, yes, I understood classification,
Right.
grouping. I didn't get the reading before it goes out, and I didn't get the explanation on regression as a type of, as a type of machine learning. Just help
Right.
me a little bit. What do you say regression is? Because I could,
Okay. So I would say the simplest way, right?
Mm.
So, okay, let me just take a step back, right? When you think of regression, think of supervised learning, right? So I said something about supervised learning, that in supervised learning, you have your data, right? And then you have a label to that data. Make sense?
Immense.
Yeah. So now all you're doing is you are trying to figure out the relationship between your data and that label, because you're creating a map between the data and the model, right? And a simple way to understand it is if you remember how you plot straight lines or curved lines or polynomials, right? On your XY axis. You understand me? So let's say um, we have a class of students, right? And there are 100 students in the class, right? And each of those 100 students, each of them has a height. One of them is 4 feet tall, 5 feet tall, 6 feet tall, blah, 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 right? And then I can now plot a graph, right? On the x-axis, I will say student one, student number one, right? And then on the y-axis, I can put in their height. And I'll do that for all of the students, right? And I'll look for patterns, right? Is it a straight line? Or is it a curved line? Or is it a polynomial, right? When I now identify the pattern or the curve or the line, the kind of line that connects the X and the Y axis, right? Now I can go out of that data and I'm able to predict, hey, if I get a student, right, that has this particular height, you know, this is going to be a variable that connects to them. And I'll just, one of the things is, I think it will be better to just show you an example, you know, because at the end of the day, all you're doing is you're trying to identify a pattern and you're like, okay, if this happen, if A happens to B and um, A1 happens to B1, A2 happens to B2, A3 happens to B3, and all of that, right? Then if I bring in a new A something, say A10, I expect that so and so B10 should happen to it. That's essentially what regression is.
I think I,
But yeah, but what I would say is hold your breath because we'll look at an example of regression
it's okay.
very
I
soon. Yeah,
understand. I
yeah.
understand. You look
Okay.
for a relationship.
You're essentially looking for a relationship and you're using the relationship about other things to predict what could possibly happen to the other people or the
Okay.
other variables.
I'm carried along. Thank you.
Okay, you're carried along. I like the way. Dr. Ngozi, please go ahead.
Thank you, sir. I want to understand reinforcement.
Yeah.
Does it mean that the data is not labeled? Then you give the machine
Hmm.
the algorithms that are not labeled.
Hmm.
Then along the line, how do you reinforce it? Because I understand that when you are reinforcing, is it after the machine must have selected, must have identified the right patterns,
Hmm.
then you now feed the reinforcement or you embed it in the algorithm you fed the machine. So I want to know how the reinforcement is carried out. Is it within the data or is it outside after it must have identified the patterns or whatever you are expecting the machine to do?
Okay, so a typical example, right, of reinforcement learning that I can think of right now is let's say you're moving from point A to B, right? And there are 100 different ways to get from point A to B, right? And you have a reinforcement algorithm, right? And you have some kind of agent. And you ask the agent, right? I need you to find the shortest path between point A and point B, right? Let's say it's just the agent just lazes around and goes through a path, right? And gets from point A to point B in 2 hours, right? But it's possible that there is a route between point A and point B that the agents can get to within, say, 20 minutes, right? So that particular agent at that particular time, right, with a 22 hours record hasn't gotten to where it's supposed to, like hasn't uh gone through, what would you call it? Hasn't achieved, it has achieved the goal, but it has done it in a time that is far longer, right? Instead
Okay.
of say getting there in 20 minutes, it gets there in 2 hours. So the agent is not rewarded at that particular time. It could be penalized, right? Because it's when it gets its results, and you've set up the rules around what you want, right? When it comes, it's not rewarded and it starts afresh. And then when it does certain things that it's supposed to do, for example, finds the shortest path to that point, you reward it. But again, to be able to understand it, and like I mentioned, I have a specific, what would you call it? Jupyter notebook where that I would actually go ahead and share it with us, though it's not very central to what we are doing right now, so that you can go through step by step For some of them, I really haven't had time because one of the things I want to do with a lot of these Jupyter notebooks is you have a line of code and then I come under and I try to explain what's going on there. I'll try to put some of that so that they are self-explanatory as you begin to go through them. So the point is to be, because everything happens within the code, if that's what you're asking, right? There's a feedback mechanism like most other algorithms, because what happens with those algorithms is, so for example, for the classification algorithms, right? Let's say you run a classification algorithm. At the end of the day, and you try to do an inference. An inference is you trying to check whether your model did what it's supposed to do. So for example, it will tell you something like my accuracy rate, that you ask it to predict something. Let's say you showed it a lot of cats, right? And it learned pictures of different cats. And then you built that model. And then to test it, right, you bring in a random picture of a cat that was not used for that training and you showed it. Often you use something like a camera or something to show it the picture of a cat. And it will say, oh, I predict that this is a cat, but I do it with a 70% accuracy, right? For you, you have decided that for me to accept that it's a cat, the algorithm or the model is supposed to predict that whatever it shows me is a cat by 90%, right? In that case, 70% is not good enough. So what do? You probably might augment some of the pictures or introduce more pictures, tweak some of the parameters and hyper parameters, and then you train that model again, right? And then you test it. You probably keep testing it until it begins to move from giving you an accuracy of 70% to something like 90%. Kind of. That's kind of but again, everything happens within the model. But you run tests, you get some feedback, and then you do something with the model. And to the point, right, that's mostly what a lot of people that are going to be involved in data science right now will be doing. A lot of the algorithms have been created. So except you're trying to solve a problem that nobody has solved, there is no point trying to write a code. But what you're mostly going to be focused in is tweaking parameters, hyperparameters, some of which we are going to talk about. What are those parameters? What are the hyperparameters? And then how do I measure the performance of those models? We would walk through all of those.
Thank you.
Okay, questions? Additional questions? So one of the things is I'm going to put more reading materials, right? In the folders. Please try to catch up on a lot of those materials because like I mentioned, most of what we do in class is not going to be in depth because we have so many things that we need to touch in class and we don't have enough time. So that's where you actually, so some of the things, what I just want to do is just at a high level introduce the concepts, but then when you do your reading, you would actually now, first of all, you won't be shocked you're seeing something you haven't seen before because it's going to be familiar, but now you can dig into more depth. So if there are any more questions, I'll take them, or else let's take a quick break and then we'll come back in 10 minutes time and then we're going to go deeper into aspects of supervised and unsupervised learning. So 10 minutes. So I will see us back in, for those in Eastern, it's 10:13, it's 10:03 now. And for those of you in West African time, I think it's going to be something like 3:13. All right. See you then. Okay, so we're going to continue from where we stopped the last time, right? And we're going to do a deeper dive. And I'm going to start by just giving us the simplest, which is what I was talking about before. I want to talk to us about the simplest form of supervised learning, because understanding that supervised learning can actually now take you into so many other things. And I'm going to do it with a um, specific example. So let me share my screen. Um, Let me see. Okay. So I hope you can see my screen. Okay. I think they can now see my application. Yeah, this is a specific slide that I just want to share. Let me share this. And I hope you all can see it. If you have any problems or you can't see anything, please put it in the chat and we can go from there. So let me share this. So one of the things, right, that most people here, I believe, have been through is the equation of a straight line. Because now to do machine learning, you need to understand some math. You can't run away from that, right? But one of the simplest things every one of us, whether you are a math or a non-math science or non-science student would have done is the equation of a straight line. That's basic mathematics in high school, right? What you have is the equation of a straight line, which is where you have y is equals to mx plus c. People write it in different ways, but at the end of the day, that's just what it is, right? So what supervised learning does is to try to model the relationship, for example, between two variables, right? And those variables are your y and your x, right? So for example, if I have y is equals to 2x plus some constant, and your constant could be 1, 2, 3, 4, 5, 6, whatever, right? It's a constant, so it's not going to change. And then you have m, your m is your slope, right? So this is more or less static. This is static. So the variables you have are your y and your x. So if I want to change my y, all I need to do is change my x, because every time I change my x, my y is changed. Change my x, my y is changed, right? So to understand all of this, you need to have to understand, supervised learning, you need to understand this basic issue. And I'm going to show us a couple of examples, right? So eventually you're going to develop a model, and then that model, you have to test that model. And I'm using this rudimentary example for you. Eventually, there's something called your mean square error, and I will show us what that mean square error means for this simple equation, right? So let's go. This is a typical example, right? High school math again, right? So if I get a couple of X issues along the X axis, right? And I look for their value on the Y axis, right? And say they fall somewhere along these lines all over the place, dot, 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 dot. And I fit a straight line between them, right? Then I can find my slope, M, right? And how do I find my slope, M? All I need to do is I will say on the Y axis, there's going to be the lowest part. I can pick 2 points. Let's say I pick a point here as my y1 and a point here as my y2. And I'll say y2 minus y1 is the difference along this line. And then I look for this point, a point here and a point here. And I'll say this is x2 and this is x1. I'll say x1 minus x2. So to get my slope, which is my gradient, all I just need to do is change in y1 minus y2, which is the difference in y1 minus y2, minus the difference in x2 minus x1. Boom. That's how I get my slope. Pretty straight, right? So where's my intercept? My intercept is anywhere where that straight line cuts through the y-axis. That's my intercept. If that line had gone through somewhere here and it was in the negative, then I'll have it as some kind of minus, right? Whatever that value is. So that's essentially how I get my M and my X. Sorry, my M and my C. That's the equation of a straight line. So I'm going to introduce a couple of concepts and then we'll come back to that machine learning somewhere in the midst of all of this. So one of the things you're going to keep hearing when you're doing machine learning, artificial intelligence is something called features. You know, you hear things like features engineering. What exactly is features engineering? These are all concepts that you are already familiar with, but maybe you did not know that's in machine learning is just called features, right? Let me give you an example. So features are individual measurable properties or characteristics of the data you are using to make predictions. Again, that sounds kind of esoterical, something out there, right? So I'm going to give you an example, step by step. Now, when you have an Excel sheet, for example, and you have all of this data scattered over your Excel sheet, right? Now, you will notice you have rows and then you have columns. Now, each of those columns, right, you know, have data in them. And that's where you have your features, right? Those columns, that's where you have your features. So normally you could have, when I say you use a data set that has at least 10 features or 10 columns, right? That's what I'm referring to. But when you have all of those features, eventually you want to get a target. There's something you are looking for, and you want to use all of the information in those columns to get the last column, which will be, for example, your target. Again, don't worry about it because I'll show you an example. This is a typical example of what I'm trying to do, right? So here, there's something you can see. You have your square feet, you have your number of rooms, and year built. This can be your, what do you call it? You are a realtor, right? And you want to build a model. Somebody gave you some data to build a model, right? So this is what you have. Let's say you have an Excel sheet with 1,000 lines, right? And let's say in this case, we would expect more features, but let's just assume we have how many features? 1, 2, 3, right? So which is your square feet, your number of rooms, and the year built. That's the only information you have. But what are you trying to predict? You want to predict the price. So if I have a room that is 2,000 square feet, it has 3 rooms, and it was built in 1995, what could the price of that house be? Now, because we are doing supervised learning, right? What you start with is, this is the label, right? You have all of this, right? But this is the answer. If I have a house that has this many square feet, this many rooms, and was built in this year, this is the price. So this is real prices of these houses. So you get all of that together, right? But eventually, when your goal is to be able to use the model that you built to predict the price of any house. So if someone suddenly tells me, hey, I want to buy a house that is 2,000 square feet, 3 bedroom, and blah, 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 I can just use my model to, even though the house doesn't exist, but I could just use my model to predict what the price will be. That's what's going on here. So your model uses features. Notice what the features are. Features are square feet, number of rooms, and your year built, right? To learn patterns in that data and then to predict what the target will be. And this is what your target is. And I just hope this is clear. So let me go to the next page. One other thing I need to mention, and I think some of us, we've already encountered this a little. If you started working and playing around with your data, there are all kinds of data, and those data, you don't treat them in exactly the same way. Now you have your continuous data, right? And your continuous data is things like age. So all the numbers, they are like numbers on the number line, right? Like age, salary, temperature. Those are all what we refer to as continuous data. Because understanding the kind of data you have, right, and how to manage it in your Jupyter notebook will be very important to you being able to understand your models, build your models, tweak your code, and all of that. So you also have categorical data like color, right? You can have all kinds of color, but that's different from continuous data. Continuous data is actual numbers like 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Those are all continuous data. Um, you know, floats, all of those are continuous data. And then you have ordinal data, right? So this is so education level, right? That's what you refer to as ordinal data. So, for example, high school is lower than bachelor's is lower than master's is lower than. So there's some kind of order to it, but it's also categorization, but there's an order to it, right? So for in the case of categorical data, there is no order to it. Red is not greater than blue, even though it's categorization. But in this case, it's categorization, but there's some kind of order to it. And then you have binary numbers. We talked about that a little bit before, when we're talking about the codes, right? Or your Boolean values. For those of you that took some of the refresher Python course, right? You have yes, no, 0, 1, true, false, blah, blah, blah. And then you also have text, image, time series, and sensor data. So all of these, you have numerical converters that can help you convert, for example, a text into numbers, because computers do not understand text, they do not understand images, they do not understand sensor data. So you have to convert all of those data. If they are not continuous numbers, somehow you have to figure out a way to use converters to convert them so that the system can ingest them, which is the whole thing about classical computers. Classical computers is really about numbers, and if you narrow down, it's about what do you call it? Your 0101, which is more or less your binary number. So if you have a decimal number, you still have to convert it to a binary number before the computer can ingest it and understand it and do anything with it. So I wanted to point that out because that's very important and central to understanding what we are going to be doing. So the next part is your feature engineering, right? Because I just showed us what features are. When you go to your columns, right? Each of those columns, each of them are features in your machine learning model, right? Features engineering, therefore, is the art and science of creating the best features for your model. So what does that mean? Because there are certain features, right, in your data that might not be very useful to the eventual prediction. It might not be useful, to the eventual prediction. And if you are able to identify what those features are, then there's no need to use them because they might be immaterial to the data. So feature engineering is, what really helps you to identify what is important and what's not important, to remove some things, or else you create really cumbersome models, right? That will be very hard to run. But then if you can strip it bare, remove all the things that are not necessary, and then run your model is more efficient and also less prone to error. So in feature engineering, some of the things you do is you select the important features. Like I just told us, some features might end up not being important. You transform those features, right? Sometimes there are all kinds of transformation that you can do to those features. Like I just, for example, this is an example of a transformation like the encoding. Even though the encoding, there's something called one hot encoding, and if you have a pen, just write it down. Uh, one hot encoding, or label encoding. Those things are very important, right? Let me look for an example of one hot encoding. So let's say um, I'm doing uh, a classification. I'm doing a classification machine learning. I'm doing classification, right? And I have, what would you call it now? In a list. Remember what a list is in Python, right? In a list, let's say I have 8 different animals, or let's say, let me make it short. I have 4 different animals. I have a cat, a dog, a chimpanzee, and a monkey, for example, right? And I've given this system all of this data to analyze it, pictures of different, I've used pictures of each of the 4 animals, right, to build a model. Now I'm trying to do inference, which is show it a picture that was not used to build the model to see if it can understand that picture, it can predict that picture, right? So if I bring, say, the picture of a dog, right? It will predict the picture of a dog, but and then at the end of the day, it's going to give me a probability that it's a dog, right? And it will also give me a probability that it is a cat. And it would also give me a probability that it is a chimpanzee. And it will also give me a probability that is a monkey. So when you have that list in your Python, right? That list, so it will give you the probability of one comma, the probability of the other comma, the probability of the third comma, and the probability of the fourth, right? But because it is, like I mentioned, I think it's a dog that I chose, right? Because it's a dog, the probability that it will be a dog might be like 90%, right? The probability that it is any other animal will be very low, something like 10%, 17%, 8%. And let's say I've placed a threshold that 90% is my threshold for saying that it is accurate. Now you notice all the other things in within your your lists are lower than 90%. So what you do in one hot encoding is, instead of, that all the other ones are false because they didn't meet the threshold, I would automatically use a one hot encoding to change them to 0 because that's false. Change each of them to 0 and only leave the dog, which is above 90, to be 1. So instead of having 0.17%, 18%, 90%, blah, 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 which probability could be 0.17, 0.18, 0.90, blah, blah, blah. Anything lower than 90, I change it to 0, and I just change 90 to 1. And I'm going to show you an example in case all my the things I've said in words don't make sense. I'm going to show you an example. But for some people that caught what I'm saying, kudos. We solved your problem, but we're going to go deeper, and you will see. I think I have an example in this slide that shows one hot encoding. So sometimes you might actually create a new feature by combining 2 or more features, you know. So look at the bottom here. It says a well-crafted features is actually what can improve the performance of your model, right? So being able to choose the right features can improve. So another way to look at it is to say that those features, those columns that you have in your Excel sheet, they are actually like clues that you give to a detective. Let's say there's been a crime, right? And the crime scene has been cordoned off, but then you have a knife there. right? You don't know who stabbed this dead person there, but you have a knife, you have some blood, you have some DNAs, all of those clues, right? The more of those clues you have and the more clear those clues are, the most likely it is for you to be able to solve that crime. So features, those columns that you have are more or less like clues. So the better the clues, if they are clear, they are relevant, and they are complete, the better the detective. In this case, the detective is like the model. The better they can solve that mystery, and that mystery is literally like your prediction, the prediction you're trying to make. So feature engineering is really, really very important when you're trying to solve a problem. So look at what are the three features that we had, right? If we were to look at them and plot them against price, right? So I'm plotting square feet against price. This is what I get. It's actually like a straight line. If I were to independently plot the number of bedrooms, two and a half bedroom, three bedroom, blah, 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 if there's a 2.5 bedroom, whatever that is. But then I'm trying to plot it against the price. You see, it's almost straight, but it's not exactly a straight line. And then if I want to look at plot the year that it was built against the price, it's scattered all over the place, right? So each scatter plot shows the relationship between one of the features and the target, which is your price, right? So, but eventually, when you're trying to build a model, what you're trying to do is, which is what makes machine learning a little more complicated than your typical, what do you call it now? Your straight line equation, right? Is that so you can have up to 1,000 different features, right? So how do you map all of these things together? That's what makes AI complicated, and which is exactly why AI exists, right? So because we are going from these simple mathematical things that we used to do, but now instead of solving, like for example, this is a two-dimensional problem, right? Your X and your Y. But if you introduce bedroom, right, all of a sudden it's an X and a Y and and a Z. So what happens if I have 10 different features or I have 20 different features? Now you can't even it becomes difficult or impossible for you to even imagine it. And that's where the issue of tensors come in, right? Because with tensors, you can arrange all of those features together, right? So to understand machine learning, you need to understand tensors because that's your way of putting all of these 2 or 3 dimensional problems and increasing the number of dimensions so that when you're predicting your target, you are actually using all of those features to make that prediction. Sebi, I can see your hands are up. Talk to me.
Yes, sir. Sir, thank you very much. Sir, in relation to the scatter plot that we have, can
Mhm.
we have the interpretation as a statistician or as a data scientist to your clients or your stakeholders?
Yes,
Thank you.
yeah, you can. I mean, and that's actually the simple part, because you can, and there are all kinds of measures with which you can interpret what's going on. But just for our single purposes here, right? For example, if we can see that there is a direct correlation between the how many square feet a house is and the price, right? There is also some kind of, the only outlier that you have is here, right? There's also a direct proportionality relationship between, but then when you come to the years, there is no direct correlation between the year it was built and the price of the house, right? That doesn't exist. But just using only one of these is not an exact predictor of what the price of a house will be. Sometimes the age of a house, right, can predict whether it's cheaper or more expensive, but we don't know what that relationship is, right? So we need to
Hello,
put
sir.
in, sorry, someone wants to say something?
Yes,
Yeah,
Joseph.
yeah, go ahead.
So that you won't go far, maybe and that I may be finding it difficult. Maybe I'll be dragging behind and behind. I'm looking at these features, these features, and when we talk about target, in the traditional analysis and in traditional modeling, there's things we call independent variables and
Yeah.
dependent variable.
Mm-hmm.
So I'm looking at these features to be more of these independent variables.
Yeah.
And I'm also looking at the target
Mm-hmm.
to be like a dependent variable.
Yeah.
So I don't know, because when we're talking about the features, I'm looking at them as a kind of characteristics, factors affecting.
That's exactly what it is. But
Factors affecting. So,
yeah. Mm-hmm.
and when you're talking about this engineering,
Mm-hmm.
the what do you call it now? This engineering,
Feature
like
engineering.
feature engineering,
Mm-hmm.
is pointing towards some of these things you thought before now, maybe where we are cleaning, maybe cleaning of data
Yeah.
and all that. I don't know, so that the spirit can remain quiet within me, so that I won't be
No,
lagging
no.
behind.
So again, everything you're saying is spot on. If you've done some statistics, it's the same thing, right? But the
Yes,
point is, machine learning just scales everything you have done to the nth degree, where n is equals to infinity. Does that
okay,
make sense? Yeah. So
yes,
is this everything you know in statistics is not challenged, right? All it's done here is that we are moving from, say, sometimes when you do like multivariate analysis or bivariate
yes,
analysis, yeah, you're
yes,
using two predictors, right?
yes,
Or
sir.
you're just using two features or three features. The question is, if I had to deal with 100 different features, right? How would I do it? Right? That
Yes,
takes
sir.
us away from the realm of humans to the realm of machines because it will really require machines to do those things.
To do those things. Thank you.
Exactly. But why I started from 2 dimension to 3 dimension to 4 dimension is most people, even there are some people that are even good in machine learning, they don't understand the nitty-gritty, how we go from a simple, straight line equation to what they are doing today. But that's the connection. So you'll be hearing people say features, features, and they have no idea what a feature is. But if you look at it from this prism, you just understand how simply a feature is just a column on your Excel sheet. Boom. So this is what I was trying to, and thank you for that, Joseph. So this is what I was trying to say, right? Somebody was asking me to explain what's going on here. For example, here, generally more space means higher prices. More bedroom also tend to lead to higher prices. But what is not exactly clear from this data is how the year the house was built actually affects the outcome or the data. So newer homes may fetch higher prices, you know? That's what we would think, but it's not always the case. And you can see it shown in this data scattered, right? But somehow, intuitively, I still believe that the year a house was built could have an effect on the price, but that effect, we haven't seen it, right? To do that, right, we have to now build a learning model, give it all of this data, and then see what it's able to predict. So this is how machine learning models see the world, not as stories or pictures, but as numerical relationship between the features and those outcomes, right? That's essentially what a machine learning model. So the next thing sees the data and how it's processed. Now, how features are processed within models, right? Understanding how features are processed in models using linear regression as an example. So now we're actually going into linear regression. And I bring this because of some people that had asked me some more additional questions about like what exactly is what exactly is linear regression. So we're going to be looking at a typical example of a linear regression, right? So we're still working with those specific example that we had. So imagine if we had this data set, same thing. And I put, you see the dot, dot, dot means like the rows could run to infinity, right? We have all of this data. So we have the price, and look at this arrow. I'm assuming that there are even more features here that we haven't included. Assume, assume that there are more features, right, that are out there that we haven't included, which, by the way, we can. So just take your time and just look at what's going on there. You see what's going on there? And don't forget your equation of a straight line, right? But assume that it's beginning to expand, because in that equation, all you have is y is equals to mx plus c. But assume, and that m, right, is like your weight, what you have here, right? That's how it's crafted in machine learning. So your y, which is your predicted price, is equals to, you assign a weight and then your square feet, and then another feature. Let's say if there was a fourth feature, it will now be W4 and then that feature. And then you can continue that way to W1000 times that feature. But then the new things that you have here will be your bias, which is your MX plus C. That your bias is the intercept, right? That crosses your y-axis. That's what you have here. So y hat is the predicted price, which we have here. W1, W2, W3 are the weights. These are your weights that the model learns, because this weight, right? Think of it like it helps the model figure out how important is square feet to price. W2, how important is bedrooms, the number of bedrooms to size. Because so if I made this 0.9 now, I'm saying that 90% of price is determined by square feet. If I make this 0.9, then this will be something like 0.05, and then this will be 0.05. Or if I feel like, okay, this has more weight, I can say, okay, this is 0.2, and I make this 0.7, and I make this 0.1. So these numbers are arbitrary. So in machine learning, right, what happens is that the machine learning, algorithm is learning to figure out, it will be trying different scenarios to find out the optimum values of W1, W2, and W3. That's what machine learning does. These are fixed values, but then I'm trying to figure out which of them has more power, which of them contributes more to this, to the final price. That's what's happening there. So the intercept, which is like your bias, MX plus C, in that case, the base value when all features are zero. Assuming all these features are zero, right? What will be my base value? One way I might look at it, I don't know how correct that is, but at least it will aid in your understanding, right? Um, Assuming square feet is not a thing and bedroom, we don't have bedroom. For now, let's just arbitrarily assume that this is the price of the land. Just arbitrarily for now, because we are going to encounter it some more. So this is exactly what's going on here, right? We are tweaking. We are tweaking these different things. Just think of someone, a DJ, right? To get the music they want, the sound, they have to tweak those knobs, right? You keep tweaking those knobs until you get what you want to get, right? And that's what's happening. So you have your square feet, you have your bedrooms, you have your year built, and then you're tweaking them. Which of them creates, and then eventually, you know what you're going to do? Once you get the weighted sum, you look at the prediction. So what do I mean here? Right? Once these weighted sums, right? let me go back. These weighted sums, W1, W2, W3, right, are going to determine whether what your prediction error will be. Because see what happens, right? Once I create that model, right, and then I now want to test it against some data that is not here, right? I will get the prediction and then I'll get that data. How well it's able to predict that result, right, is what will tell me whether W1, W2, or W3 are correct or not. And I will show us examples. Let's just take it slowly. So I was just using this to demonstrate what happens on a mixing board. To get that real sound, you have to tweak those weights, right? And those weights is what would eventually mean what result you get. So let's look at biases, which is what I was talking about, right? I'm like, what exactly is that bias? Which is your C, which is in a straight an equation of a straight line, it's your intercept. So in machine learning speak, what exactly is it? So in machine learning, especially in linear models, right, and neural networks, bias is a learnable parameter, right? And when we say learnable parameter, right, it changes, it can change, right? And it's added to the weighted sum of inputs before adding an activation function. Don't worry about this. We are going to touch on what is an activation function, because gradually we are going into machine learning. What's a weighted sum? You have already seen what a weighted sum is, what is bias, and then what's a learnable parameter. So let's still go back to our really simple equation. So there are things that are called neurons, right? When you go into neural networks, right, they are just specific points, right, where things around the feature are determined. But I'll just grab that in your mind. Just remember the issue of neurons, right? So this is an example of an equation for a neuron. This is an example. So, and then there is also what we call an activation function, and just hold that in your thoughts. So notice, let's assume in our example, right? This is our example. Price, your Y. So assume that Y, right, is this, right? Because what's going on is, to really get the Y, I need to put all of this into an activation function. Just take a minute and look at what I'm saying, right? Let me go back here. To really get the answers of all of this, I need to assume that I'm creating a bracket called activation function, right? And I put all of this inside that bracket, right? I need to perform an activation operation on them before it would finally give me what my predicted price is. So let me go back there again. So essentially, all we are saying is, this is Z. Just take all of this and put it in here. So your Y price is equals to activation, then all of this inside there. And I will explain why that is going on. You will understand gradually as we go. So why exactly do we need a bias? Now, the bias allows the model to shift the activation function left or right. Remember, I haven't told you what an activation function is, but you will see what it is now. Without it, the model is restricted to functions that always pass through the origin, which is extremely limiting. What does that mean? Let me go back here and show you something. So remember this, right? Without this activation function, without this bias, your data is always forced to pass through to the 0, 0 point. But we know that in real life, right, data can be anywhere. It can be scattered anywhere. And when you're drawing a straight line through that data, right, you're moving that data in such a way that it will pass through as many points as possible. Now, if it's going to pass through as many points as possible, that means that um, data would experience a slope that might be different than what a straight line through zero would require, right? So an activation function actually helps you shift that line, a bias rather, helps you shift that line. So this is why you have the intercept here, which is your bias. It helps you shift that line from zero. Because most things in life, when you model them, do not pass through zero. So which is the point here? Without it, so the bias allows the model to shift the activation function either left or right. Without it, the model is restricted to functions that always pass through that origin, which is extremely limiting. Now, imagine if you had a smart door, right, that opens only when the weighted sum of sensor inputs exceeds a threshold. The bias is the threshold itself. So an example is if you had a sensor in the house, right, and you said, hey, I don't want this, I want this sensor to only turn on, right, after we have hit 40 degrees, right? So you can create that buffer so that, hey, this thing doesn't turn on until we get to 40 degrees. So that 40 degrees, right, is your buffer, you know. So it creates an opportunity for you to have some space before doing something. So let's go back to our simple regression, right? So the formula for your simple regression, we already talked about it, right? Is y is equals to wx plus b. There are different things that I use, mx plus c, whatever, but you just have to make sure you understand what is being talked about. So, but I'm using W and B because we are trying to transition from simple regression into machine learning because specific terms are used in machine learning. So in simple linear regression, y is equals to wx plus c. The weight, which is our w, controls the slope, right? The bias controls the intercept. Like if we are trying to do a one-to-one comparison of what it is. So without bias, all lines are forced to go through the origin, which is rarely ideal. So in neural networks, right, which is your machine learning. So this is what actually happens, right? You have your z is equals to wx1 x1 plus b is equals to your activation function. So bias acts like a tuner or knob. Remember, I was showing you how the guy on the mixer, helps turn things, right? In the particular case of neural networks, right? The bias acts like a knob that allows each neuron to activate at the right time. So in your machine learning, one of the things you see is these are all neurons. And so you put in your features. Remember those features that you have on your Excel sheet, right? You put them in, and this is what you call your input layer. And this is what you call your output layer. And in between, right, you have your hidden layers. And this is where all of the magic happens, right? If you want to go into machine learning, this is all the things you're going to learn. So, but the features, for example, that's what I'm focused on now. You put in all your features here, and then you get your prediction here, right? So each of them is referred to as a neuron. So it says that in each neuron, right, what happens is you have your weight and then you have your x. Remember your x, what your x is, right? This is your x. So what you have is essentially what's going on. So each of them is like their own linear regression, simple linear regression equation. That's what's happening here. So you have this plus this, right? But eventually, this summation means as many of them as possible. That's essentially what you have. So it gives the model more flexibility to fit the patterns in the data. which is we're talking about the activation, right? It helps it to activate at the right time. Instead of activating exactly at 0, just like I gave you the example of the thermostat, you can set a thermostat and say, hey, I want this to keep cooling until you get to 70 degrees and then turn it off, right? That's some kind of activation. So you're not starting from 0, but you are activating at a particular point. And these neurons need to activate at specific times, right? And that's what the activation helps it do. So just like weights, biases are initialized randomly at the start of the training. So when you have a model in your Jupyter notebook, right? You have to decide what your bias is going to be. You're going to start with some kind of value. So it's initialized randomly. You can put in whatever, but then as you begin to run your model, your result will tell you how to tweak it, whether you increase it or you decrease it. And those things are things that you really can't explain until you're actually running the models. So what happens is that you begin to train the process. That's what helps you learn the optimal bias value that would help minimize the error. And I'm going to talk some more so about that later too. So look at, for example, your bias, right? So look at, let's say this is your formula for a simple regression, right? Eventually, each of these, look at where the bias is. -4, right? 0. Remember, this is your 0 line, right? So assume this is your X and Y axis. Remember, this is your 0 here, and this is your 0. So this line, right, this linear function is going through the 0, 0 point. What if we had a line where if to fit all of the data, it will go under it, right? Then where does it cut? That's what you'll be checking, right? Where does it cut the y-axis? It cuts somewhere around 4, and that's why we put it at -4, because it's cutting. This is cutting at 0, and this is cutting the y-axis somewhere here, which is like 3. So that's why we have different formulas. So that's exactly what bias does. It helps you shift that line to wherever you want on the axis. So what we have here is what I explained already, how the bias can shift a model output.
Excuse me, sir.
Yeah, go ahead.
Please, that last page. I'm not sure I was seeing what you were saying.
Sorry, I can't hear you.
I said, I'm not sure I was seeing what you were saying.
Okay,
When
go
you were
ahead.
saying that,
Yeah, go ahead.
Yeah, when you said we're seeing -4, I wasn't seeing -4 at those intersections.
Okay,
So I don't know if you want to point that out again.
yeah, I totally understand. I think the reason you might not be seeing it is because this graph was drawn in such a way that the lines are thick here. But just remember, this is your 0, 0 point. So if you look down here, you're going to see 0. Do you agree? And if you look here,
Yeah.
you're going to see 0. So this is, traditionally, this will be your thick line. Makes sense? So, but these are your lines for each of those, right? So let's go back. So where does this line intercept with the y-axis? Can you see it? Where
I'm
does it
trying to figure
intercept
it
with
out.
the y-axis? This is the y-axis. Where does it intercept? Here.
That's 0.
No, it's not 0. Look at your 0 point here. Remember, you need to be looking at this, right? Does it make sense?
Oh,
Yeah. So
okay. Now I
that's
see.
why I know why you were seeing it that way, which was
Okay.
perfectly legitimate, right? Does
Okay.
everybody understand what she's talking about? Because she's talking about something really important.
Yes, we understand it.
Okay. All right.
Thanks, bro.
Yes, sir. Yes, ma'am. So the question will be, again, I'm trying to use the things you understand to pull you into the realm of machine learning, right? Bias in linear regression, are bias and intercept, right? Really the same thing in linear regression? In simple terms, yes. Remember in linear regression, we kept using the word intercept, right? But intercept is really the same thing as bias, but in machine learning, it's referred to as um, bias. So the question is, are bias and intercept really the same thing? In linear regression and in simple terms, they are the same thing. There's a little difference. In linear regression, bias and intercept refer to the same thing, which is this, right? Both describe the value of y when x is equals to 0. So let's say if we plug in 0 here, both of them, that's your starting point, which is your bias in either case. However, in machine learning, especially neural networks, each neuron has, sorry. In machine learning, especially notebooks, each neuron has this. You see what's going on here? Each of those neurons I showed us, right, is like an individual straight line equation of its own, right? But remember, all physical phenomena are not necessarily straight lines. Some of them could curve and all of that. But in this particular case, bias is not just a regression intercept. It allows every neuron to shift its activation, just like in an intercept, right, actually shifts the line, right? So it helps you with the activation. But in deep learning, you can't really call it an intercept anymore because you are no longer fitting a straight line. You are actually shaping a complex function, right? So it's easy to call it an intercept. But imagine if it's a curved line and all of that. That's why we don't call it an intercept. We call it more of a bias. So,
I have a question, sir.
yes, sir. Go ahead.
Okay. In explaining the difference between bias and intercept,
Hmm.
can we look at it this way that for each neuron,
Hmm.
because each neuron has that means that what we have as an activation function here is like we can say that like millions of summation uh, of neurons like this.
Yeah.
Is that the reason why so it means for the bias for the linear regression that's just an instance, but in this case now we are having millions, you could have millions of such neurons
You are
together, so
you
to
you
be
are you are correct. Again, remember what I was talking about features, right? So if we're doing a simple regression, we're just using one feature, right? What if we have 100 features?
yes sir,
Yeah.
yeah.
So and then eventually, so even if these concepts are still primitive, right? You might not deeply understand them, but as we begin to go deeper and deeper, you will now begin to see them. But a lot of people don't even get this background, and they just get into that, and they just see something called bias, and they just start using it. They don't know what it really means. So you're definitely thinking in the right direction. So So, in summary, if you're dealing with linear regression, right, which is what we are doing at this particular time, a bias is the same thing as an intercept. But if you're dealing with machine learning or deep learning, bias is the same concept, but it's used in every neuron to add flexibility to those neurons, right?
Yeah.
Eventually, I'm going to show us what activation functions are and why you use activation functions, right? Because they do the same work that your bias, for example, your intercept, right, will do. And they do that using a bias. Now, so in summary, right, bias is an extra parameter added to the weighted sum of the inputs, right? Its purpose is to allow the model to shift predictions and improve the flexibility, and then it represents the model's default output. In that particular case, what if all the inputs are 0, right? Then that's your starting point. And it's trained like every other parameter. And like I mentioned, you start with a particular bias, and then depending on what results you're getting, you keep tweaking it until you get there. And in the most part, right, when you're doing machine learning, except you are a developer of machine learning algorithms, most of what you're doing is tweaking those parameters until you get the results that you're looking at, which is why I'm like, you just need to learn Python so that when you see those codes, you can understand what they are, and then you can, with more and more study, you can know the ranges of numbers that can be used for any particular trainable function, and then you can enter those numbers, train, get your results, test, go back, and keep doing the same thing. So now I go to activation functions, right? How much time do we have? Let me see how much, because this is important, especially for what we are going to be doing that I mentioned, right? The capstone, no, the certification or certificate program that we're going to be doing closer to the end. But then it serves the dual purpose of helping us to better understand linear regression too. So an activation function is a mathematical function applied to the output of a neuron. Remember, we said y hat is equals to activation, then in bracket we put z, where z represents the linear equation that you had then, right? So that's what your activation. So it's a mathematical function, but it's applied to the output of a neuron. And I'm going to show you exactly why we have to apply this activation function to the output of the neurons, right? And when I say the output of the neurons, I'm just essentially talking about, for example, in the specific linear regression case that we're talking about, that output is the price of the house, which is your y hat. So that's the output, right? So in machine learning, why do we have to apply an activation function to that output? You're going to see why. Now, the reason is a lot of activation functions. What an activation function does is it introduces non-linearity to the model, right? Allowing the network to learn and represent complex patterns in the data. What does that mean? Remember when the first example that I gave you, right, about the house and the rooms and all of that, right? You notice it's a linear function. In other words, it's straight, right? But a lot of things in real life are not straight, right? Those functions, that's a straight function. But a lot of things in life, when you model them, right, they would give you complex functions that are curves, and all kinds of really interesting things, models, right? But what activation functions do, right, is you're using that same formula, but it will now help you, right, introduce non-linearity so that you can get the specific curve that you're looking for, to that model, allowing the model to learn and then represent complex patterns in the data. Without this non-linearity feature, a neural network would behave like a linear regression model, no matter how many layers you stack on it, right? So, and that's why essentially as you move from just having one, let me go back and show you something. So like this example, right? This thing is certainly not linear. When we're talking about year built, it's certainly not linear. This is some kind of complex function if you are to capture as many points as possible, right? So this, how do I use the same formula, but I now give it the ability to represent non-linearity? That's kind of the simplest way I can think of that. So that's what activation functions actually help you do. So activation functions introduce nonlinearity, which enables neural networks to learn complex relationships, patterns like if this and that, or only when this exceeds a threshold. Remember, I was talking about how sometimes in your house you use your sensor, what do you call it? Your thermostat to set, okay, my AC behave in this particular way when you get to this particular temperature. That's not linear, right? That's non-linear because it's not just going straight, right? If it comes to a particular point, it can take a detour, right? That's what that is about. Activation function helps you achieve that. So sometimes you have this some decision boundaries that curve or bend, right? That's all what helps do all of that, the activation function. Now, non-linearity is one of the most powerful and important ideas in neural networks. That's very important. So non-linearity means that the function does not produce a straight line when graphed, and its output is not a direct proportion of the input. That's what non-linearity essentially means. Because we are used to things just being straight, but in real life, all of those things are not necessarily straight. So look at a typical straight line here, right? Something is going through zero. But there are certain things, right, that you have that go this way and then they bend that way, or you have functions that go this way and then they curve up this way. These are all different kinds of function. Look at the blue one. It starts everything before zero, it goes this way, and then all of a sudden it takes a proportionality, right? And these are all activation functions. So there's what we call the ReLU, there's what we call the sigmoid function, and then there's what we call the tan H function. So if you've done any kind of machine learning, you'll be familiar with all of these functions. But and this is what they would look like. But we might not help you understand and applications of all of these functions in the class today. But as we keep going, the good thing is you've learned about them. I would encourage you, this week, take some time, just read up on some of those different functions. What are activation functions, the different kinds of activation functions. As you do that, by the time we now get into using it, you would understand why we use it. All right. So these are all of what we have here, right? I wouldn't be talking so much about this. But we'll talk about this some more. Let me see if there's anything I need to touch on right now. Okay, let me just go ahead. Probably spend some more time. I don't know where we are with time. Okay. Let me talk about this some more, and then we'll go to our, what do you call it? To our Jupyter notebook, and then we'll discuss regression a little bit there. So see what's happening here. For example, look up for ReLU, right? Let me go gray. So first of all, this is your straight line, right? Everybody understands the straight line. Once X is increasing, Y is increasing. That's a straight line. So that's easy. But what's going on here? Look at your ReLU. Negative for zero for negative inputs increases linearly after zero introduces a threshold. So let's say, and I'm going to show you an example, right? There's an example after that. But let's say I have a set of data, right? Like -1, -2, -3, -10, -11. And then think of a list in Python, right? I have all of those numbers. And then after that, I have 0, then I have 1, 2, 10, 8. So essentially, I have negative numbers and I have positive numbers, right? So if I plotted that graph, right, it will give me something like this. If I have negative and positive numbers, because all of this is negative, right? But let's say I'm trying to model something that behaves in this way. If I put in that same figure output, right, into a ReLU function, guess what it will do? It will throw up something like this. Because everything that was minus, all those -8, -1, it will convert all of them automatically to 0. And that's what you have here. And then after that, all the positive values, it will deal with them normally, proportionally. That's what ReLU does. So there are certain times, right, in machine learning when you need to get those kind of outcomes. So you feed in that data, and then the activation function will now change those things, right, and give you a completely different output. Same thing is happening here. So for example, in sigmoid function is an S-shaped curve that squashes all inputs between 0 and 1. You know, great for probabilities. So let's say I get a bunch of numbers, right? You know, and let's say I get a bunch of numbers. If I want every one of them to fall in between 0 and 1, right? I run them through a sigmoid function, right? And it will bring everything, and it will put every one of them somewhere along this path, 0 to 1. And this one does the same thing, but in this case, it changes everything between -1 and 1. Again, just understand the general concept. When we work with examples, you're going to see how and why that's relevant. So this is a summary, right? What the graph shape looks like. It's linear for everything between x and greater than 0. So it does a linear thing. But for everything from 0, um, uh, for when x is less than or equal to 1, right? It changes it to 0, which is what I showed us here. It changes everything to 0. Anything less than that, it changes it to 0. So this is just a summary of what I just discussed there. So let's look at an example here, because when you start doing your neural networks, these are some of the kind of things you're going to run into. Let's assume the following weighted sum, right? Let's say we have this function, which we already know. But let's assume that at the end of the day, when we run, impute the necessary data, we get this result, right? And this is a list, right? Your list is -2, -0.5, 0, 0.5, and 2. The point is, and somebody now asks you, I need you to now transform this, right? Because we're trying to get our y hat, and our y hat is equals to activation of x. Now we know what of z. We know what our z is, right? So we want to be able to run this through different activation functions, ReLU, sigmoid, and tar, right? So what will it convert them into? So let's come here. This is all the values of z, which is what I have here, right? These are all the values, -2, -0.5, 0, 0.5, and 2. This is all of it here. So if I run it through ReLU, right, -2 will turn to 0. -5 will turn to 0. If you still remember what I was talking about, that everything in ReLU, everything that is minus, you know, is automatically converted to 0. Everything that is 0 remains 0, and everything that is above 0 remains the same. So if I run my result through a ReLU activation, right, I'm going to get this. But if I run it through a sigmoid activation, what am I going to get, right? I'm going to get these numbers. And then if I run it through tar, this is the numbers I'm going to get, right? And all you need to do is spend some time looking at it, because it's actually very, very straightforward. Because all you're doing, for example, in sigmoid is you want to squash all of those numbers into 0 to 1. And then when you run it, it's going to give you for this tan h, you're trying to squash everything here into a range of -1 to 1. The question is, why would you want to do these things? you have to hold your breath until we actually start using them, in trying to build models. But what I want you to do is that you have heard about what these activation functions are and what they do and how they convert numbers. So this is a discussion of what I just talked about now when you get the slide. So sometimes there is a concept called sparsity, and this is one of the reasons why you actually create these activation functions, because sometimes, so one way to think about it is the cells in your brain, right, are always firing. If everything in your brain fires, all the neurons in your brains fire at the same time, right? Each time they see something, right? If all of them fire at the same time, you're going to go crazy. Maybe that's what's happening to people that have some specific classes of mental illness, because all of their neurons are firing at the same time. So one of the things activation functions help you do is, let's figure out some of those features, right? Which is the neurons, right? That do not immediately contribute much to getting our target results. Instead of creating noise, right? And you have something like 0.1, 0. Why not let's just turn it off and turn it to 0? And let's focus on the things that contribute most to that output. That's exactly, and that whole thing I explained right now is what we call sparsity. So sparsity refers to a situation where most neurons output 0 or do not activate for a given input, right? And I just hope you're getting some of this. So essentially what ReLU does, right? If you look at it, this is the summary. If Z is less than 0, we make it 0. If Z is greater than or equals to 0, we make it the same value, So you look at this, I want to leave you with, okay, let me just do this lastly. Maybe I'll probably come back to these slides later because of time, because I don't want us to not do our Jupyter notebook, but let me just touch on this. Let me touch on this because this is going to be important to our conversation. We might come back to where we stopped on this slide next time, or at least you do the reading. Most of it is, I set it up in such a way that they are self-explanatory. And if you have any questions, you can reach out to me. And I think we might be coming back to this slide in the future to discuss some things. So remember this weighted sum, right? The W that we talked about. At the heart of many machine learning models, especially linear models and neural networks, is the idea of weighted function, right? We already talked about what those weighted functions. It helps tell you which assign probabilities or weights to each of those values, depending on how important they are to the final output, right? So in linear regression, we have something like this. And then in neural networks, we add an activation function. And the purpose of the activation function is to help, convert what would have been a linear function to the right function that you need. So the prediction is either the weighted sum, right? Or its transformation. This is the transformation of that weighted sum. So the reason I wanted to continue this is because of prediction. Prediction is really, really very important in linear regression, right? How does weighted sum, right, relate to prediction error? So let's say one simple formula for prediction error is, let's say this is an actual value. Because it's supervised learning, we know what the actual value is. So in the example that I gave to us, we already have the prices, right? So, and then I create a model and I ask it to predict something, right? And and I ask it to predict something and it predicts something, but what it predicted is different from my actual. Let's say in this particular case, right, we have one of those prices, right? And I've given it all the values and I gave it different weights and I ran the model and it gave me that the true value for the parameters that I gave it, right? The actual, we know that the actual value is $300,000, but then it actually predicted $280, right? So the error will be the actual, which we know, and what it predicted, which is 20. So which is your Y? Your Y in this particular place is the true value. Your Y hat is the predicted value. So your true value minus your predicted value gives you your 20,000. Okay. Now go with me. Now, if your weighted sum is off, your prediction will be off. Why do we have this happening here, right? This is happening because somehow the prediction that we did not predict this well. Because if you had predicted it well, it would have been 300 times 300. So at this point, when you now see this error, that means that your W needs to be, your W1, W2, W3, and W4 need to be tweaked again. And that's what your machine learning model does for you, right? It does all of those, it runs it again, and then predicts different values of W. So that's what happens, right? Now, the model measures this error using what we call a loss function, right? That error, it measures it using what we call a loss function. And there are different kinds of loss functions. And when we start going deeper into the machine learning of data, you're also going to be encountered by a lot of those loss functions. And your loss function, the simplest way to look at your loss function, because I still know a lot of people that are in machine learning that use loss functions and do not know what loss functions are. Loss functions, this is the starting point of what your true value minus your predicted value is. This essentially your, yeah, go ahead, Jessica.
Yes, Doc. I wanted to ask, so even like with science, when we are doing experiments, we have like errors associated with the data. And
Correct.
so in this case, the actual value is like a specific data, but then you were saying that we should expect the error to be zero. Is that ideal? Because there should be some level of associated error. Is there like a threshold range of an allowable error to which you can conclude that the model has predicted it right?
That is an excellent, super question. Yeah, so frankly, in science, right, most times you don't expect 100% because there's always some kind of noise. But so think of it this way, right? As hypothetically, you're gunning for 100%. So eventually, those are some of the things that we're going to go into later as we go in, because you hear something like overfitting, right? Where a model is able to predict something and it's predicting, you know, let's say you use some kind of training data, right? After you've predicted everything to give you 100% result. You now introduce data that was not used to train that model, right? And then it will give you 50%, right? What happened was that the data that you used was tightly hugging, it did not actually produce a good model. That happens too. So
Okay.
in terms of the threshold, you will have to decide what that threshold is. So for example, I can decide, and it depends on the criticality of what you are. So if I'm trying to create a model, right, for say, I want to create a model where a robot, right,
Mm,
that is embedded with AI can do surgery on someone. The criticality of that is so high because any mistake, the person can die,
yeah.
right? So the threshold there is going to be different from the threshold of some other mundane task.
Mm,
The threshold for a driverless car right, is going to be completely, so it depends on what it is, and you are going to introduce that threshold. Well, question, excellent question.
Thank you.
Yeah. So,
Another question, sir,
yes,
related.
sir.
So taking it from where she stopped,
Hmm.
can we say that in reinforcement learning,
Hmm.
that in that case that the system will continue to iterate to reduce the error until probably it approaches zero?
So it depends on what you are, um, because sometimes, right, sometimes in machine learning, it's not just, you're not trying to fix an error, you're trying to also figure out, the best path, the shortest path, and all of that. But again, I would say everything tends to zero. Everything you're trying to do is to tend to zero. And you can see some of these functions, right? Is it like the exponential curve or something? Where you have um, the curve, right? It's starting somewhere at the top and then it's almost going to touch zero, but it doesn't really touch zero. So I would say the same thing applies, irrespective of what you're talking about. It's the same thing, you know. So do we have models that are 100 that get 100% accuracy and are good? I have seen those, but they are very, very rare. And the issue is, can you even rely on those models? You know. So, but that's why it talks about error minimization. That's why we talk about error minimization. So, what we should, please, there's someone that is creating a feedback for us. Can you turn off your, if you're not talking, please turn off your, yeah. So the goal is not necessarily to eliminate error, but to minimize error. So you repeat until the error is minimized. So normally you start with a random weight. You compute the, you start with put in the weights, and then you compute the total of the weights, and then you use weighted sum to get your prediction, and then you compare that prediction to the true value, what we just got, and then you get the error, and then you use that error to update the weights, and then that's how you keep reducing error, future error. And that's essentially what I just described right now, is actually what machine learning is. You start from some predicted value, and then you keep going through that process until you come to a point where this thing is behaving in a way it should behave, so that if I try to use it to predict anything in the future, it essentially gives me the answer.
Okay, sir. Can I just add one thing, sir?
Sure, sure.
I'm actually trying. I'm actually trying to link everything you have taught us.
So sorry, turn on, you've been muted. Please turn on your stuff again. I'm sorry. Jimo, hello?
Okay, sir. Thank you.
Yeah, go
So
ahead.
I said I was trying to link everything together, what you have taught us today,
Right.
and then my mind just went back to the that idea of reinforcement. I
Mhm.
mean, given the fact that the system is actually working on feedback,
Right.
you are not teaching it. It studies the pattern and it
Correct.
tries to come up with an algorithm, and with that is able to predict. And
Yeah,
then when it makes mistakes again, then that goes into the feedback loop again, and it continues with self improvement.
absolutely.
So so the question that came to my mind, okay, so is that the kind of that means that the process of error correction is in I mean that's automated, inherently automated, is that right, sir?
Oh, that's kind of, so I would say semi-automated, because that's where it comes, the issue of parameters and hyperparameters come in place, right? If you don't have the right say hyperparameters, it could keep going in a loop and never tend to minimization. You see what I mean? But the process itself. So for example, I would say I want you to run 1,000 epochs, right? which is 1,000 cycles of running through, right? And then I will give it a certain number of the learning rates and all of that. And it begins to run. And each process, to your point, is self-correcting and self-correcting and self-correcting. But then when it finishes running those epochs, right, you now check the result and you see that it's getting about the same thing. If you go again and ask it to run again, it might keep giving you that result, right? But what you want to do is now, that's why I say it's semi-automated. You now go in there and tweak your parameters and have it run again. And you keep going, doing back and forth. So you're essentially working with the model or with the machine until both of you arrive at an answer that is acceptable to both. So, correct. All right. So, in essence, I've touched a little about a loss function, but what I just wanted us to know is what a loss function is. We are going to continue this conversation later, so I'm going to go back to the Jupyter notebook and we'll discuss there a little bit, because we are running out of time. But these are some of the things we are going to be focusing on later, right? To expound on the idea of the loss function, which I've already told you is essentially the difference between the predicted value, the actual value, and the predicted value. But that's the general concept. But it gets a little more, it gets deeper, right? As you begin to look at multiple neurons and all of that. So in this particular aspect, we actually talked about what a loss function is, right? And then these are different ways of measuring it. And I just gave us, this is the simplest one that most of us are familiar with, where, let me see if just give me one moment, because there's a lot to cover here. So we can't cover that here today, but I think by next week we'll talk more about loss functions and the MSE. MSE is the particular one most of us must have used, where let me see if I can. Okay, I think it's in the other slide, right? We have a situation where you have a straight line, right? And you have dots, your points, right? So vertically, the difference between your point and that straight line is the error, right? And then you gather total all of that error, right? And you divide it by the number of points. That will give you the average error. So that's what happens. That's what I was trying to show you here, but I don't have a diagram for it. Go back. So that's how the loss function, especially if you're using this, that's how it works. But then once you get your predicted value minus your actual value, then you square it, right? And then you divide it by the number of summation. Just means how many of them. So y1 minus y1 hat 1 minus y1, you square it plus y2 blah 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 to y number, or whatever the number, right? And then eventually, let's say if there are 100 of them, like 100 different features, you now divide it by 100, right? That can give you a reasonable estimation of your mean square error. But why do you include the square, right? It's actually trying to help exaggerate, how you have outliers, right? It's trying to help exaggerate large losses, large errors, especially when you have outliers. That's what the mean square error does. And you can read up on this. There's so many videos you can watch on it. And then there's also the mean absolute error. But in this particular place, right, it tries to treat all of the errors equally instead of exaggerating large errors. So it depends on what you're trying to see. That will determine what kind of loss function you use. And then as you go into classification, there are all kinds of loss functions in classification. There is the binary cross entropy, categorical cross entropy. We'll talk about some of those later. And more importantly, would also use examples. You have the softmax output, again, what I'm trying to do is not to make you masters in this, but to introduce you to the concept so that when you have notes and you're reading them, they would make sense. This is actually an example of a classification problem. I know we haven't gotten to classification, and it shows how it's done outside a computer. Let's say let's do it on paper so that you can see how it's done. That's where I actually went through step by step to explain how a categorical loss function happens before you now get an opportunity to run it on a code. So I think we're going to stop here for this. Any questions? So hopefully we'll come back maybe next week and we go look at discuss some of the things we already discussed today and then go deeper into some of those machine learning concepts. You know, for linear regression, because I know those are very important and central to data science. I'm going to show us. I'm focusing more on this machine learning part because you don't really have a lot of good people explaining it, at that base level. But I'm going to put a couple of videos around linear regression, logistical regression, and then would have our slides where you can understand it, implement it, and then we'll keep going deeper and deeper as we take off into neural networks and all of that. So questions?
I had a question which is outside of what we discussed in class today.
Yeah.
So basically, this is Jessica from Python class. I'm not in the Discord group, so I just wanted to know how I could get access to like the slides and the videos. Yeah.
Okay, I will just talk to me after this.
Okay.
Yeah. All right. So any other questions? I know this is a huge data dump, especially for people that are new to these concepts, there are a lot of new things, but trust me, it's not that complicated. It only happens the first time you see it and maybe the second time, but as you begin to go into it, it becomes progressively easier. Okay, so let me share my screen and then we will do a bit of those codes, I believe. And some of the things that are on the slide we've already done, so I'm going to skip some of them. So if you can see my screen, right, I'm kind of focusing a little on predictive modeling, regression, and evaluation. But in this slide, you notice in the beginning, I didn't just talk about predictive modeling or regression. I actually started with sorry, I didn't focus on regression, but I started out with predictive modeling so that you understand what predictive modeling is. So these are the objectives when you read that, right? Understanding supervised learning and the concept of regression, which to an extent, if you are been in the class, you would understand what supervised learning is. Then the next thing is we want to implement a simple and multilinear regression using Python. And then we can interpret regression coefficients and outputs and then evaluate regression models using MSE. I just talked to us right now about MSE, RMSE, MAE, and R squared, right? So those are all ways you measure error. That's why I said you can actually evaluate those regression models using each of those error measurement tools, one of which I just showed us there. So first of all, and then recognize the assumptions of linear regression and diagnose model performance. So first of all, I talk about what predictive modeling is. I know we've touched on that a little bit in the past. It's the process of using data and statistical stroke machine learning techniques to forecast or estimate future outcomes based on historical or current data. So you have current data, but you want to extract insight from this current data so that in the future, if you encounter some related data, not exact, but related data, then you can actually use that model to predict it. So that's what predictive modeling actually is. So at its core, right, it tries to answer the question, given what I know now, what is likely to happen next, right? So these are some of the things predictive modeling can help an organization do: anticipate trends, optimize operations, personalize user experiences, reduce risk, and improve decision making. And these are some examples. Banks use it, for example, to detect fraud like your anomaly detection. If you studied the patterns of customers, right, and then you see someone doing something out there, the system would automatically flag it, right? Um, oh, Hospitals predict patient readmission. Let's say you have hospital data, right, and you know that in one of your features, if a certain thing happens, right, there's a high likelihood that the patient will come back and say, I wasn't, I'm still sick, right? So if you have a lot of data, you can actually build a model where you can, if a certain thing happens, you know that there's a 90% likelihood that this so patient is going to come back in 2 weeks, right? And that's the beauty of machine learning. And then, of course, you see other examples. And this is how predictive modeling works. First of all, you have to define your problem, which is why I told us to define our problems for our project. You have to collect the data. You have to pre-process the data, which is, are there any missing data outliers? You do some normalization, encoding, and then the feature engineering, which is where you create, select, or transform those variables that improve the prediction. Then the model selection, then you have to choose what model you're going to use, you know. So here we're going to be working with some data where either we generated the data here, and then we'll choose a model that we can use to test it. And sometimes, you can use different models and compare their results, and you find out that a specific model is actually better for what you're doing. That's all part of your data science work. So these are all kinds of models. And in the beginning of the class, I also showed us some examples of different models, Um, and then the next thing is you feed the model on labeled training data, and then model evaluation. That's when you use some of those tools that I mentioned. And these are all some of them. Some of them we haven't talked about, but like your F1 score, your AUC, ROC. We're going to hopefully talk about all of this later. And then your deployment. Then that's where you deploy your model, and then you can monitor and update your model over time.
Reaction, sir.
Yes, sir.
Sir, please, a little reaction. These videos, with especially with the respect to font sizes.
Mm-hmm.
After when you record them, and then during I don't know, my own personal reading, the fonts are always tiny. I don't know whether you'll be blowing them up a little before posting to us, because we just sometimes strain to be able to get them, to be able to read them. Even as I'm looking at them now, they're also tiny, even at this without reproduction yet. Sorry, sir, for the interjection.
No, you're good. Are you using a phone? Do you
I'm
watch
not
it
using a
on a
phone.
phone?
I'm with my PC.
Okay.
The full window.
Yeah. So I'm not sure if I know how to blow it up after, but if anybody knows, just let's talk after this.
But
It
I
might
feel
be
it should
helpful.
be at the point of production.
Yeah,
Depending
but
on the font size you use, sir. Is this 12?
uh,
Is
is
this
it
12?
12?
Yes, sir.
Yeah, I think it's 12. So I think the challenge, because it's not like what would you call it now? It's like, so for example, if I was using a slide, it would be easy. But if I have, for example, what you have here, blowing it up can't fit it on a page.
Okay,
So
sir.
I
It's just a
think
reaction.
so. No, your reaction is valid. I'm just thinking of how to solve the problem. But so do you have access to the Jupyter notebooks? Because that's where you can actually see those things. So when you
Yes,
open
sir.
up your
Yes, I have.
video,
I have. I'm
yeah,
sure we installed Anaconda.
yeah,
Yes,
exactly.
sir.
Hello, sir.
So yeah, go
Sorry,
ahead.
sir.
Mhm.
Can I react to that a bit?
Yeah. Mhm.
All right, sir. After you have downloaded the document, sir, you can zoom it in. you can zoom out using your PDF. That is possible. So maybe you have a look after downloading. That's not from the original now, from the downloaded copy.
Okay.
It's
No,
possible to zoom it.
no. So
Then
he's talking about the videos. Is that what you're talking about too?
no, document, the document.
Yeah, yeah. So
Like,
for the documents, all of those you can actually zoom, but
Well, sir, I think it depends on the system is using. Actually, you can zoom in video. Like the system I'm using now, I can zoom what you are doing now. The video,
right.
I zoomed it. So it actually depends on the system is using.
Yeah.
You can zoom in, you can zoom out.
Yeah, I think on my part, the difficulty is if I expand this further, then you can't even see everything that's in, you know.
Yes, sir. Since
yes,
it's
you
not
are
a general
right.
problem, we can
Yeah.
manage, sir.
Okay.
Yes, sir.
Yeah.
Thank you.
Yeah, sorry for
Perhaps if it's in a full view, if he changes his screen size to full view, maybe probably that will help.
right. Yeah, but for me, I think the most important thing is to have your your notebook open so that you can see what's going on in your notebook. Because even if you can't see what's going on here, you can hear what I'm saying, but you can see everything on your notebook and you can follow on the notebook. That's I do highly recommend, you know. All right. But I think I'm going to do some investigation on how to, because I know there are people that do it, especially for their YouTube videos. But I would figure that out. That hasn't been a focus of mine recently. So this is an example. This just gave us a typical example of different kinds of, where is it? Where am I? Okay. So regression and classification, the difference, right? So in regression, we are talking of real numbers, continuous, but in classification, we are talking of classifications. That's what's happening. Here we want to predict a number, and in this place, we want to predict a category. That's the main difference between regression and classification. And then these are typical examples of models that you can use. Here you have linear regression, you have logistic regression, typical outputs. Again, you're getting numbers, but here approved and denied, cat, dog, blah, blah, blah. And those are all examples. So now, just give me a minute. Let me just go this way, go this way. I don't know if this is going to help a little bit. Okay. So this is what we have here, right? Oh, this is where I stopped. Now imagine a scatter plot of house prices versus house size versus house price. So all we are starting with here is your matplotlib, which is the application or package, right, that helps you plot graphs. So that's what we start with. And then NumPy, which is numerical Python, we imported it and they've been installed on the system prior, right? So you come in here. Let's say we create a NumPy array. And again, if you're not familiar with NumPy arrays, all you need to do is go back to week 0. There are a couple of videos that teaches you about NumPy. And NumPy is just numerical Python. It just helps, it's a package that helps extend the ability of Python to work with numbers, right? And what that means eventually is that you can create arrays out of numbers, right? And this is an example of one of the arrays. So these places, we gave this, maybe let's just assume they are square feet, right? 100 square feet, blah, blah, blah. How many of them do we have? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 houses. And then we're assuming that each of them, right? The prices are given in 1000s, right? So this is 500, $150,000, 180,000, 200,000. So these are the house prices, and these are the house sizes, and these are the house prices. So now we go use a particular method, a NumPy method, right? That is called polyfit, right? Let me reduce this. So let me come here. I think polyfits. Yeah, this is what polyfit does. I hope you can see my screen though.
Yes, sir.
Yeah.
Yes, sir.
Yeah. So NumPy polyfit function fits a polynomial or a specified degree to a set of data using the least square method. So what it's actually using is the least square method. And like I told us, there's a abstraction that happens in programming. Once you go type in your polyfit, which is this, yeah, your polyfit, NumPy polyfit, all it does is that it uses least square method to be able to run this, right? To do this regression, right? That's essentially what it does. So we start by saying our coefficient is equals to NumPy. You use your polyfit, and then what data are you trying to work on? You use your house and your house size and your house price, right? That's what you have here. And then the next thing we go look at is where is it? Your degree. So what degree of polynomial do you want to fit with, right? So because the polynomial can be a 1-degree polynomial, which is like your straight line, 2-degree, 3-degree, depending on what kind of curve you are anticipating, right? Because you need to have some kind of hypothesis of what you're trying to do. And that's why you have this one here, right? This particular one is similar to that, but what it does is actually helps you to define the function. And I didn't include, so let me include this as resources so that when you're reading, in case you want to read some more about this, right? You can just come here, resource 2, and that will be your, because if I spend time explaining every single thing there, it becomes difficult, but I want you to be able to understand what's going on at a micro detail so that you can. So this would be, first of all, NumPy polyfit. And then this is poly NumPy. Sorry, poly ID. So just reading here will help you understand what's going on for this, right? And that's it. And every other thing you see here is just your plot function, how you plot, right? So your plt dot scatter just tells it, hey, I want it to be a scatter plot, which could be dot 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 dot. That's all it is. And then you tell it what to plot, right? The color in which you want it to plot, because you can change these colors. And then the label, what kind of label do you want? You fit in all of that information here, right? So here it says actual data. Then this is the method that actually makes it plot. And then you tell it what you want it to plot, right? And then you label all of that, right? And that plot, right, that we're talking about is the solid plot. The first one is this scatter plot, then the plot function. So there's dot scatter, there's dot plot, and that's what plots this. And then these are just your title, your what you want written, or the label on your X and Y axis and all of that. And then show will just print it out. So it's pretty straightforward. But what it does is that it creates a regression model, essentially this, and then that's what you get. So the blue dots, which is the scatter ones, are the, the actual house data. So that for here, this is my size. If I want to buy a house, right, that is 150 square feet, right, I would expect that the price is going to be something like 200,000. If I want to buy a house that is like 250,000 square feet, I would expect that the price will be somewhere around 300. And so this all by itself is a model, right? So if I'm trying to figure out, right, hey, if I want to buy a house that is 2,400 square feet, that's not part of the data, right? But I can just use this model and just come here and be like, okay, 240 is going to be somewhere there. If I move it up, boom, it's going to land in here. So I should expect to buy that house at $300,000. So that's the simplest form of machine learning model that you can have. Yeah, so that's an example of a machine learning model. So that's what you have here, right? An example. And then the second example I have here is a classification example, right? So this is what you will call your regular regression. But then when you want to do classification, right? And that's what you do, like your logistical regression type thing, right? That's an example. So let's just quickly run through that. So this is regression, but this is classification, right? And all of these fall under your predictive modeling. So same thing, right? We do the same thing that we did there, but this time we're looking at exam scores, right? And then we are including a label to it. Now look at what's going on here. I have all these scores, 40, 45, 50, blah, blah, blah. But let's say I have defined my own threshold. I said anybody that makes less than 60 has failed, right? So remember the whole thing about encoding, right? Instead of coming to say pass, fail, pass, fail, pass, fail, pass, fail, pass, fail, I just come in here and I create a label for this, right? And I tell it, okay, because this person made 40 is 0, where 0 is fail and 1 is pass. Somebody made 45, 0, 50, 0, because 0 represents fail. And then I will keep going. And then once I get to 60 and above, 62 is pass. That's why I have 1, you know? So that's how you can actually represent it, because this is the only way the computer itself can understand what's going on. So this is a case of classification, right? I'm giving it this data and I'm labeling the data to be like, okay, this is what this means. This is what this means. This is what this means, right? So what else do I have going on here? So I decide to plot, right? But then I've been able to write this code, right? But notice there is a particular function I use here that is called zip. This zip function, it pairs elements from the two lists into a tuple. So you have this and this. This method zip actually makes sure there is a pair, that this aligns with this aligns with this, and that's what's happening here. For score, label, right, in zip, exam scores and labels. So this is your way of zipping both of this so that they are directly connected, that each of those elements within the array, say elements within array that is exam success, maps to the label. That's what that function does for you there. So, and then we now say if the label is equals to 0, do this. Else, then write this. In other words, if it is 0, which we already have, do this. If it is 1, do this, right? Right? And what does it do, right? You have your score, your label, and all you need to do is go look at your dot scatter plot method, and then it will show you what each and every one of these is actually doing there, right? So you list all of this, which you have in your method score, and then you now said if this, else this. All of this will be like your typical if statement, if else statements. But what's happening here is that all of it was now put on a straight line. And if you're comfortable with Python, you should be able to go ahead and put an if statement on a straight line, because that's essentially what they are doing here, right? And then you run it. And then you have another situation here, because I'm just putting out some of the things that might not be very clear on what they mean. So you can see this method here too, PLT AX V line. Again, it's very easy for you to just copy that. Anything you don't understand there, copy that, and then just go to Google and try to understand PLC method in Python. Oh, so you see what it does? It essentially draws a straight line. So let's go back, because I put it there. So this function draws a vertical line across the entire height of the current plot. Notice there's a line that was drawn here, right, to divide the fail and the pass, right? So that's what's happening here. And because of the way we label this, because this kind of looks a little bit like what I was talking about when I was talking about those functions, where you can want things to be separated in a certain way, 0 to 1, or I want an S curve and all of that. Because we used 0 and 1s here, that's why when you run this, they are tightly separated at this point and at this point. And then you now use that function that I just showed you, that method that I showed you to create this line. Going back to that method, right? When we just come here, right? I now write x is equals to 60. Essentially what it is saying is that at the 60 point mark, create a line to separate. That's what it has done. All right. And then the style of the line, dot, dot, all of that. And then you call it what label am I giving it? Decision boundary, and then you list it that this line is a decision boundary. So it's very straightforward. And then you do your plot here too. That's all that has happened here. And then with that, you can predict what's going on here. So this is an example of a very basic binary classification model. All right. So again, it's not very complicated. And then to read it and understand it, the red dots, right? They are for fail scores, any score that is less than 60, and green dots are for pass, for everything greater than or equals to 60. That's what you have here. And then, this is logistical regression, same thing, So logistical regression is a type of classification, which is almost like what's going on here. But I think we are going to stop, because I don't know whether some people have appointments and I don't want to keep everybody here. But once you go into this place, the same things I've done there just applies, but it just shows, same thing, and I even talked, there's one thing that is not very clear that some of you might struggle with, which is this reshape. Why do we have this function, right? We have the data X. Then I put dot reshape. I try to explain what's going on here. So it's very easy for you to understand. And then you can go through all of the code. Again, if you run into something that is kind of complicated, we can talk about it maybe either on the platform, or you can reach out to me, or when we come to the next class. But that's a lot to dump on you all today, but I think we need to stop, and we'll be gone. Thank you, everyone. Except if there's a question or you want to talk to me. Yeah, all right. Thank you. Appreciate it.
Today was tough. Thank you, sir.
I know. Thank you.
Thank you.